So now we're going to learn how to take derivatives of the trig functions. So I'm going to start with sine of x, and I'm going to use the definition of the derivative to derive what the derivative of sine of x is. So I've got sine of x plus h minus sine of x of h. Right, so now I need to do something about this sine of x plus h. So that's not too bad, because I can use a trig formula, right? Sine of a plus b, right? So it's going to be sine x cosine h minus cosine x sine h, and then just minus sine x here. But then what I'm going to do now is rearrange these terms. Oh, I'm sorry, this is supposed to be plus here. Okay, let's get that right. Okay, what I'm going to do is I'm going to rearrange the terms, because I've got this sine x and this cosine x, and then I've got this other sine x. Well, the limit is on h. It doesn't really care about the x, right? So I'm going to try to rearrange it so I can pull that stuff out. I can't really pull it out of everything because I've got two things here, right? I've got, first of all, I've got my sine of x, and then that is multiplying these two terms, right? This would be cosine of h minus 1, and then the next one would be cosine of x times sine of h, all over h. So what I'm going to do is break this up into two limits, this one and that one. Okay, and maybe this is really two steps. We're going to break it up into two limits and then pull out the sine and cosine. But I'm just going to write that as one step, because I'm going to pull the sine out of the limit, since the limit is on h. And so the second limit then is sine h over h. So now what we have here, in order to evaluate this, we have to evaluate these limits. Well, both of these are special limits. Especially this one is not easy to evaluate. So I'm not going to go through the proof of this. There will be a proof of it in the extra materials as usual. But this guy, we can prove this using a geometric argument and the squeeze theorem. So that's typically how it's proved. And what we already talked about this limit, it was a while ago though. It was when we first just started to learn about limits. So remember, this isn't the sine of 1 over x, this is the sine x over x. No, now it's h. But if I draw that, it looks like that. And because of course it's 0 over 0 at 0, right? So it's not defined there. You have an open circle. But everywhere else, and it does in fact really look like it's going to 1 on the graph. And with that, with that construction, the geometric construction, then we can prove that this goes to 1. And if you don't want to watch the video, it's also, that proof is in your book. So that's a special limit that it was kind of important to know, in fact. We'll talk more about that in a separate video. This limit, it turns out, goes to 0. This is much easier to prove than that one. Basically, this one has a little trick. You multiply top and bottom by cosine of h plus 1. That means the top part, and you can use it becomes like sine squared, right? Because then you have a cosine squared minus 1, and this will become minus sine squared, right? So basically, you can do that way. And there's still a little bit more work that needs to be done with that, but this one you can do pretty much algebraically. This one, it's really a little bit of a bear. So, having said that, now we can find out what we really want to know, which was, what's the derivative of sine x, right? So the derivative, this whole thing goes to 0, and that's just 1, so the thing that's left over is cosine. So the derivative of sine is cosine. So that's the big thing, right? So let me write that up here. I'll try to keep them. And then if you do the same thing for cosine, finding the derivative of cosine, it's very similar, only slightly different, right? Because this is a little bit different. But with a very similar proof, you can also show that the derivative of cosine is negative sine, right? So we have to be a little bit careful. You have to remember there's a negative here. The derivative of cosine is negative sine, not sine. But you'll see with our patterns for the other ones that is a pattern that we see. The minus goes with the the cofunction, right? So the minus goes with the cosine. So let's then next do, well, we have those two, we can now talk about tangent, right? Well, tangent though is, we don't have to do it with the definition of the derivative once we have sine and cosine, right? Because we also have the quotient rule, and we know that we can write tangent as sine over cosine. So that, in fact, is very convenient. We don't have to mess with any fancy limits or anything. We'll just go ahead and barrel through with our quotient rule, right? The derivative of tangent is going to be the derivative of sine x over cosine x, right? So the bottom squared, and then the bottom function times the derivative of the top minus the top times the derivative of the bottom. Okay? So we can work, and now we know these, so we can just plug it in here. This is cosine squared x. This is going to be cosine x, derivative of sine is cosine, so another cosine, minus sine, the derivative of cosine is negative sine. But you can see what you have on the top here now. I've got cosine squared x plus sine squared x in the top. And bottom is just cosine squared. But cosine squared x plus sine squared x, that's the Pythagorean identity. We know that's 1. So that is the derivative. And of course, 1 over cosine is secant. So this becomes secant squared of x. So the derivative of tangent is secant squared of x. And sort of, I'm going to not do it again, but in the same way, you can do the derivative of cotangent, right? Because cotangent is cosine over sine. The derivative of cotangent is going to be negative cosecant squared. So again, it's the same pattern, secant, but gets a minus. And then the third one is, of course, the derivative of secant, right? So the derivative of secant is secant x tangent x. And then the derivative of cosecant is negative cosecant x cotangent x. So those are the 6. Whoop. Could have put it over a little bit. But those are the 6. Okay? And I'll leave them up there. And for the next video, I'm going to do a couple examples, basically using all the stuff that we have done this week. Oh.